Hello everyone, welcome to another episode of Thinking Modular. I received some requests to implement in VCV Rack some of the patch ideas I previously show in my videos where I use Reactor. And today I'm gonna replicate the third episode. So I would like you to listen for a moment this patch that I have already assembled here. So at this point I'm not changing any parameter, it's just the machine playing by itself. And of course I can change some parameters in order to affect the system. So as you can see, every time I change a certain parameter, I'm interacting with this complex system and is answering me in a different way. But all the time, the machine presents a very logic behavior. It presents a certain repetition and a certain variation, which actually is very useful to create music. So my videos is about nonlinear circuits and also about feedback, and I would like to bring you a concept that is related with these two concepts, that is cybernetics. So cybernetics, I'm gonna summarize, is just the core concept of the discipline is a circular causality or feedback. So for instance, imagine that you have a sensor like a thermometer, and this thermometer has a certain threshold, so it means that it has a temperature set. So if the temperature goes below that threshold, it switch on the heating system. And at some point the heating system is going to affect the environment. And this is going to have a reaction feedback to the sensor again. So as soon as the temperature goes higher than the threshold, then the system switch off. So there is actually an interaction in the feedback. And this is the very beginning of what we could say artificial intelligence, or a sort of intelligence. This is only possible through feedback, because there is a constant communication, a constant interaction in the whole system that is built here. By introducing this idea of cybernetics and nonlinear circuits and feedback, you can start creating very interesting patch with just a few models, as you can see. Let's try to start replicate this patch. So I'm going to delete the models that I don't need now. So I want to start from scratch. So I'm gonna leave only the models that are not part of the circuit or are not important for actually to understand the circuit. So I have this one. This is just to control the level, because it's connecting here in the mixer, and then the mixer is connecting to the output. And then I also have here a resonator, because I want to color the sound at the end, and I'm gonna mix with the result from the VCO. Okay, and I also have the scope It's very important to have a scope in order to track your signal and understand what it's happened behind the scenes. So let's start. First, we need a sound source, and I'm going to use this VCO. So I'm going to connect the triangle wave. So it's a very simple VCO. It has like the octaves, and then you can tune it. And it's very simple. So the first step that I want to do is I want to connect my VCO to a comparator. And this comparator is going to generate gates, and this gate I want to modulate my frequency. Okay, so I already creating the first feedback loop here. So let's bring a comparator. This comparator looks complex, but is not. So it has 3 inputs, A, B, and C, and then it has several logic operations. Okay. For instance, A equal to B equal to C. Now it's sending 5 volts, so it's like saying it's true, because if 0 is equal to 0 and is equal to 0, is because it's true, right? So then you have several algorithms there, as you can see. But the one I want to use, that is the one that is more common to find in comparators, is this one. So it's like you have a certain threshold that is going to be the C, and every time the signal goes higher than that threshold, it's going to generate a gate. It's going to say that is true. So it generates a gate. It opens a gate. And as soon as it goes below that threshold, then close the gate, because then it's false. So, but first of all, I have to discard this first left equation here. And this would be very easy to do. I just have to ensure that my A is always equal to B. Okay, and now I need to connect on the C my threshold. So for these, I'm gonna use I'm gonna bring here an attenuator. Okay, this attenuator from Befaco, and this is very simple. It has an offset, and I can send fixed values until 10 volts and also minus 10 volts. Okay, so this is going to be actually my threshold, my fixed value. So I'm going to connect these on C, and now, as you can see from the scope, is already generating the gates. Okay, so now my threshold is at 0. So of course, every time the values go higher than 0, the gate opens and is true, and it remains open until it's not true anymore, when the signal goes below 0. And then, as you can see, I can change my threshold to the positive range and also to the negative range, and this affects the shape of this sort of square wave. Okay, but now I want to do something else, because I want to amplify this signal. I want him to reach the 10 volts and the minus 10 volts, because I want a more drastic modulation in order to later on have some range to modulate the amount of modulation. Okay, so for these, I'm going to bring these sort of mixer attenuator, because this has a little bit of gain. So if I connect the output of the comparator here, and I connect on the scope. Now is at 0, but as soon as I open until the maximum, you can see that it actually reached the 10 volts, right? As you can see. So now I multiply the signal here to 10, and then is reaching the 10 volts. But now I have to bring the signal back to the negative range by subtracting it. And I want it to set in a middle ground, more or less here. But now in order to reach the 10 volts, I need to connect the signal again in the second channel, because this is a dual channel. And I'm going to amplify even more the signal by bringing back a little bit of gain. And now I have my comparator tuned to the range I want. And now these I gonna connect in the volt per octave, because I want to use an exponential frequency modulation, and I believe that this one is only linear. And now if I bring my level up, I have to connect it here. So is already doing something. Okay, good. So now I want to go to this is already a first feedback connection. So now I want to create a kind of if I consider this the heart, now I would like perhaps to create a brain, something that resembles some logic behavior. So I'm going to bring this dual function generator from Befaco, and what I need is to create a communication between these two models, and this model is useful for that. If I connect my VCO, let's take off the modulation now. If I connect my VCO in the input A, and then from the output A, and then I have to switch to the middle position, because it's the one that tracks audio rate. What I have is actually a copy of the signal, and a copy of the signal that I can actually affect without affecting the original signal. So if I increase the rise, as you can see, it changes the signal, and also the fall in the same way, as you can see. So I can create interesting variations of the original signal here. I also want to use the second channel of the function generator, but I want to use it as a cycle. So if I connect here, then I have to switch these to the upper position that it says cycle, and then I have to trigger, so it initiates the loop. And then of course now the rise and fall are at 0, so it's actually generating a triangle wave. But if I increase the time of the rise, it starts doing more a ramp, and also I can increase also the fall. So now we have again a triangle wave, but with longer cycles. Okay, so now what I want to do is that I want to, and bear with me, I want to, the first channel, to modulate the fall time of the second channel, and the second channel I want to modulate the fall time of the first channel, but I want this modulation to be dynamic. So I would have to create a device that modulates the amount of modulation, and this device is going to be actually modulate with the information of the signal of the first channel. So as you can see, remember the cybernetics, here we have a interaction. So let's start by building this. So I'm going to use this second channel attenuator here, okay, because it is free. And I'm going to connect my output from the channel A, and this attenuator is just gonna set a certain amount of modulation, so I can put on 100% or less. Okay, and I can also invert the signal, and I also can bring it to the positive range or negative range. So this amount of modulation, as I told you, I want to modulate my fault time. And now if I connect the second channel on the scope, as you can see, if I start opening my attenuator, as you can see, it's starting affecting the signal. See? Good. Now, this I just want to use as a fixed value. I just want to set a certain amount of modulation. Now, the second interaction, I'm going to do through a VCA. So the VCA give me the opportunity to choose modulation, exponential modulation or linear modulation. So what I'm going to do, as I told you, is I'm going to connect the output B in the input of the VCA. Okay. And then this output is going to control the fault time of the first channel. And it's already changed here. But now I want this modulation to be dynamic, and I want to be dynamic accordingly to the signal that I have on the first channel. So for this reason, I have, for instance, I'm going to connect in the linear input the second output. Okay, and now we have a signal that more or less resembles the original signal, but with much more variation, and these variations can be very drastic. So now, to finalize this interaction, now what I want to do is that I want to modulate the amount of modulation from the comparator to the frequency modulation of the VCO. So for instance, I'm gonna have to connect this output. This is the model where I amplify the signal to the 10 volts and minus 10 volts, and I'm going to connect here on the input, and the output goes to the volt per octave. And now if I bring my signal up, this is just control the amount of modulation, as you can see. But I want this to be dynamic, and I'm gonna choose, for this purpose, I want the second channel to affect this modulation. So as you can see, is already presenting logic behavior. So now to finalize my connection, I want to color my sound. So I'm going to use this resonator that everybody loves, that is from Mutable Instruments. I'm going to connect here on the output of the VCO. Good. And now at this point I have these values fixed. And these are actually two values that are very important, because it's the ones that is going to create even more dynamic to the sound. So what I'm going to do is I'm going to connect the first channel, for instance, to modulate my frequency. and the second channel I'm gonna modulate the structure. And now, as you can see, it starts reacting more dynamically. This is just attenuation. Good. And that's it. Now I have my system complete, and now it's up to you to start changing some parameters. So I can change here the offset. For instance, I can increase a bit here the fall. Of the rise. I can try to switch in between exponential and linear because it gives me different behaviors. Okay. So now it's just about experimenting and setting some parameters. So this is actually based on the concept of cybernetics, because we have several devices. We have certain thresholds that trigger certain behaviors, and we have cross modulation. We have feedback. So the different models are actually aware of it happens in the whole system because they are connected. So somehow the VCO is being modulated by the comparator, and the comparator is generating a signal accordingly to the VCO. And then there is a copy of the signal in the first channel of the dual function generator that is affecting the cycle of the second channel. But from another side, the second channel is also affecting the first channel accordingly to the behavior of the first channel by using this VCO. And from another side, then the amount of modulation that comes from the comparator is also being modulated by the second channel of the dual function generator. So we actually have a kind of a complex loop around these three models. And then you have certain values, fixed values, that change the behavior. And then of course you can also color a bit the sound in the way you want. So that's it. I hope you enjoy, and see you in the next video. Bye bye.